Welcome back to the Deep Dive. This is the place where we dig into documentation, technical notes, and research to pull out the key, actionable insights you need. Today, we're getting into something foundational, the blueprints for really solid software, design patterns. And these aren't just, abstract academic ideas. They're proven solutions, refined over years, for the common problems you run into when you're building anything complex.
Exactly. They're the foundation for code that's flexible, that's maintainable.
Okay, so let's unpack this. Our mission today is to really distill the core ideas behind 7 key patterns from our sources. We've got singleton, decorator, iterator, observer, strategy, command, and state. We want to get past just the definitions and really get to the why of it all. Why do these patterns actually make your life easier down the road?
Right. For anyone trying to, level up their skills, seeing these patterns in the wild in a real professional code base, it's about instantly getting the architectural intent. They teach you how to manage complexity, how to reuse code, and maybe the most important thing, how to build a flexible system.
And there's a theme that seems to run through almost all of them.
Oh, absolutely. It's all about clever decoupling, making sure different parts of your system can talk to each other without being completely tied together.
So a small change in one place doesn't just cascade into chaos everywhere else.
Precisely. It prevents those catastrophic ripple effects.
Okay, let's jump right in with a big one for decoupling, the observer pattern. This feels like it's at the heart of any modern system that handles events or notifications.
It really is.
So the idea is you have one main object, the subject, and it's holding some important piece of state. And then you have this dynamic group of other objects, the observers, that are just watching it. But the key is the subject doesn't know anything specific about them.
Right, which is why people often call it the publisher-subscriber model. I think that's a bit more intuitive. You have a publisher that sends out a message, and then any number of subscribers can listen in.
And that's what's so powerful.
What's really fascinating to me is how this connects to the open-close principle.
Open for extension, but closed for modification.
Exactly. You can add new subscribers, new listeners all day long without ever having to change a single line of code in the publisher or any of the existing subscribers. It's just open to being extended.
Okay, but that raises a question for me. A classic trade-off, right? If the decoupling is that clean and the subject is just shouting into the void, doesn't that make debugging an absolute nightmare?
That is the perfect question. And yes, it absolutely can.
I mean, if I change something in the publisher, how do I track which one of 50 observers suddenly broke?
You've hit on the core trade-off. Loose coupling is great for maintenance, but it makes tracing the execution flow much harder. Your debugging tools have to be good because you lose that certainty of knowing exactly who is calling whom.
Got it.
But the benefit usually outweighs that cost. I mean, think about a social media app. One event, a user posts a photo that can trigger a dozen different things.
A push notification, updating a cache, logging the action.
Right. And you want all of those to happen without being dependent on each other. That's the observer pattern in action. It's how that dice game example in the sources, Zonk, can work. Multiple score displays, all watching one dice roll.
Right. Okay, so moving from that kind of external state monitoring to internal data, let's talk about the iterator pattern.
Yes.
Yeah.
It's almost invisible in a language like Python.
Exactly. It's just baked right in. But it's so important. The whole idea is giving you a standard way to walk through a collection of things, a list, a dictionary, whatever, without having to expose how that collection is actually built.
It is a huge win for abstraction. In Python, it's all about those, the iter and next methods, the iterable protocol.
So my code doesn't care if the data is in a list in memory or if it's being streamed from a database cursor one record at a time.
Not at all. The code consuming the data, the code that's looping over it, stays exactly the same. The iterator pattern just completely abstracts away the structure of the collection. You only have to care about the elements inside.
It's basically the abstraction of traversal.
It is. And in a team, that is invaluable. The back-end dev can swap out a data store, and as long as the new one still provides a valid iterator, the front-end code never even knows anything changed.
That separation is key. Now, let's pivot a bit to patterns that are all about behavioral flexibility. There are 2 that often get confused. First, the strategy pattern.
Classic. A textbook example of abstraction in object-oriented programming.
So strategy is all about having one problem, but multiple different ways to solve it, multiple algorithms.
Right. Maybe you have different ways to sort data or different ways to encrypt something. Each of those solutions or strategies gets its own object.
And the main class can just pick the one it needs at runtime, dynamically.
And that choice is usually based on real-world concerns. trade-offs. One algorithm might be super fast, but use a ton of memory.
While another is slower but much more lightweight, better for, say, an embedded device.
Exactly, and the strategy pattern lets you swap between them seamlessly without rewriting your main application logic.
The sources had that image filtering example. You could have a high-quality, slow filter strategy or a fast, low-quality one for just generating previews.
Same pipeline, different strategy.
Now let's compare that with the command pattern. On the surface, it can look similar.
Very similar, but the intent is quite different. Command isn't really about choosing the best algorithm.
So what is it about?
It's about packaging an action. It wraps up a whole request into an object, so you can do things like queue up requests, log them, or, and this is the big one, support undoable operations.
Okay, so strategy is about how to do something, like quick sort versus merge sort.
Yes.
And command is about what to do and when, like save file or print document.
You've got it.
Yeah.
And if we connect command back to the observer pattern.
Observer is passive. It just gets notified after something has already changed.
Right. But command is active. The commander object is actively making things happen, queuing them up, executing them.
So if I'm building a text editor, the undo button doesn't call the undo function directly.
No, definitely not. The button press creates an undo command object. That object goes onto a queue that lets you log it, maybe execute it later, and, crucially, it lets you save the previous state so you can actually perform the undo. Command gives you that whole management layer.
That idea of strict management is a perfect segue to the state pattern. This is where, for me, it gets really interesting. This is a pattern that lets an object literally change its behavior as its internal state changes.
Yes, and it's all based on the concept of a finite state machine, an FSM.
And we're not just talking about a simple on-off switch here.
No, not at all. An FSM defines a whole set of possible states, and more importantly, it defines the only allowed transitions between those states. It's very rigid.
And the goal is to get rid of those huge, messy if-else blocks in your main object that are always checking, if state connected, then do this. If state disconnected, do that.
Right. You push all of that logic into separate state objects. Your main class just holds a pointer to whatever the current state object is and delegates calls to it.
And the most important part.
The most important part is that each state object knows which other states it's allowed to transition to. It governs itself.
And that rigidity is essential for things like parsers. Compiling languages, interpreting JSON, or, like in that amazing example from the sources, parsing real-time GPS data.
The NMEA 0183 language, yeah.
But I mean, think about the stakes there. You're trying to navigate. A mistake in parsing isn't just a bug. It's potentially dangerous, corrupt data.
For sure. The NMEA message format is incredibly strict. The parser has to follow it perfectly. So it starts in a state, maybe waiting for start.
And it sees a dollar sign, a dollar. Only that character can trigger the transition to the next state, say, reading talk or read.
Exactly. And that state knows it should only see two characters, like GP for GPS. If it sees 3, or a number, the state itself knows that's an invalid transition and throws an error immediately.
Then it moves on. It reads the message type, like GLL, and then transitions into reading all the data fields.
You get to a reading latitude state, which expects a very specific format, 37 degrees, 23.2475 minutes.
And after that, it must transition to reading longitude. If the data stream is corrupted and sends the timestamp next, the FSM just rejects it.
Right. It fails early and safely. You get the timestamp, the status character A for valid, and then finally it sees an asterisk. Then that transitions it to the very last state, reading checksum. That state's only job is to read those last 2 hex characters and validate the entire message. The state pattern isn't just about flow, it's about enforcing structural integrity.
That focus on structure is a good lead-in to our last 2 patterns.
Let's do a quick look at the decorator pattern.
Sure, in Python, this is just everywhere.
It's the @ symbol we see all the time. The idea is to extend a function or a class without actually modifying its source code.
It's a really flexible alternative to subclassing for adding responsibilities. You just wrap the original function with new functionality.
Like logging. I want to log when a function starts and stops, but I don't want to clutter the business logic with print statements. So you just add @log function calls on top of it. Or maybe @require sadmin for a permission check. Clean and modular.
Perfect. And finally, let's talk about the singleton.
Ah, the singleton. Popular in languages like Java or C++ for making sure you only ever have one instance of something, like a database connection.
But our sources had a really strong take on this for Python.
A very strong take. In Python, the singleton pattern is almost always considered an anti-pattern.
That's a bold claim. Why is that? Why is it standard practice in one place and bad practice here?
It really gets down to what is idiomatic for the language. In Python, we don't really need the complexity of a singleton class because we have modules.
Right, when you import a module, it's only executed once.
Exactly. So if you need a single global configuration object, you just define it in config.py and import it everywhere. You get the single instance guarantee for free without all the boilerplate of the formal pattern.
So trying to enforce it the classic way just adds complexity for no real benefit.
Pretty much. The Pythonic approach is simpler and achieves the same goal.
Okay, so what does this all mean for someone listening? We've covered a lot of ground here really fast.
We have.
We had the observer for decoupling events, the iterator for abstracting access to data, strategy for choosing algorithms, command for managing actions, and state for governing behavior with an FSM.
The big takeaway, the summary, is that these patterns are all about building systems that are maintainable and extensible. They help you respect principles, like the open-close principle.
They let your application grow and change without collapsing.
Right. They are tools for managing complexity. So adding one new feature doesn't mean you have to go back and rewrite 5 old ones.
And to leave you with a final thought to mull over, we talked about how the state pattern uses that finite state machine for the GPS message. The real power isn't just in parsing the correct data, it's about rejecting the bad data. So consider this. If a corrupted or even malicious input stream tries to mess with the structure, maybe it skips the longitude field entirely, how does the strict predefined transition logic of the state pattern inherently protect the system? Think about how defining only the allowed paths forward is what prevents that bad data from ever getting processed in the first place, ensuring the integrity of the whole system from the very beginning.